Hey everyone, how are you? We're going to be continuing with seasons today and then just talking about another few phenomena caused by Earth's revolution around the sun. And then we're going to do the intro to the moon. And over the next couple weeks, we're going to be wrapping up with all the moon stuff. So remember that we're focusing on the sun, Earth, moon system and all of the phenomena that are created by all of the motions of the sun, the earth, and the moon. Okay, so just to wrap up what we were talking about the other day, the reasons for the seasons. Okay, so number one, the Earth's revolution around the sun. Okay, but not just the revolution, because remember, it's the revolution coupled with the tilt of the Earth on its axis. Remember that if there was no tilt, there'd be really no seasons. It would be the same weather and climate all year long for certain latitudes. Um, the tilt of the axis is what gives us seasons. Also, the fact that the axis is always parallel to itself. So that's called the parallelism of the Earth's axis. Um, Remember that it's all about the insolation. So that tilt creates differences in intensity of insolation and duration of insolation. So number four is when there's more daylight hours, there's more insolation and there's a warmer time of year. So that's the duration of the insolation, or how many hours per 24-hour day is the sun above the horizon. Okay, when there's less or fewer daylight hours, there's a shorter duration of insolation, and the earth and the land and the water is warming up less, and that creates the beginnings of the colder time of year, the winter season. And the intensity of the insolation. So how direct are those rays? Are they perpendicular to Earth's surface? Are they hitting at a steep angle? Or are the rays of the sun hitting at a shallower angle? Okay, because when it's a steep angle, those rays of the sun are concentrated in a smaller area. When it's a shallower angle, those rays of sun are spread out over a larger area of Earth's surface. Okay, so the sun's rays are more direct or perpendicular to Earth's surface in the northern hemisphere during our summer. So we're coming up on the day, June 21st, when there's the greatest intensity of insolation and the greatest or the longest duration of insolation. That's June 21st. Now, if we were going to be getting into meteorology and climate, we would be talking about, well, if the rays of the sun are most direct or perpendicular or near perpendicular in June, how come that's not the hottest month? And essentially, the short story is that there's a lag. The water takes time to heat up. So if you go to the beach, you know that when you go in the water in June, it's much colder than if you go in the water in July and August, because that water takes a long time to heat up. Okay, so that's kind of like the reasons for the seasons. Okay, and let's just get into our diagram. So being able to look at this diagram, just look at that North Pole, see where it's pointing towards the sun. That's our summer. That's Northern Hemisphere summer. Okay. Here's what I was talking about before. Here's a full beam falling on A where it's more perpendicular. It's over a smaller area. Here's the same beam of light spread out over a greater area. All right. That intensity of insolation explains something about the North Pole, because right now we know that everywhere above the Arctic Circle is pretty much receiving close to 24 hours of daylight. So if the duration of insolation is 24 hours a day, how come the North Pole doesn't get any warmer than it does? Well, the sun is out all day, so the duration of insolation is there, but what's not there? What doesn't the North Pole have? It has the duration of insolation. It does not have the intensity of the insolation. Okay, so everywhere above the Arctic Circle, 24 hours of daylight. Here's nighttime on the Arctic Circle during the summer. Okay, so that intensity of insolation just isn't there. So even though they have the duration going for them, they don't have that directness. Okay, so let's look at the day-night patterns on Earth. Okay, so remember that in the Northern Hemisphere summer, what's lit up for 24 hours? The North Pole, Arctic Circle up. And what's dark for 24 hours? The South Pole down. Okay, so what we're going to do is we're going to look at, where is it? Here it is. Okay, we're going to look at this. This shows you the changing pattern of daylight as the year progresses. Okay, I'm not going to pause it because when I pause it, the dates get messed up. So here's summer solstice. What was lit up for 24 hours? The North Pole. Here's December and January. What's lit up for 24 hours? The South Pole. Around the time of the equinoxes, remember that the terminator line, that's the day-night line, is lined up with the poles. So that's when the lines are vertical. So this is the changing amount of daylight on Earth's surface. So when it's up like that, North Pole is tilted towards the sun. When it's straight up and down, that's the equinoxes. And when it's tilted, when it's light at the South Pole, that's when it's our winter and the Southern Hemisphere's summer. Okay, I'm going to change this to daily right here. That would be us. See, the red dot is us. That would be us in November, right after the equinox. And you see that the day-night line is not perfectly up and down, not perfectly parallel to the longitudes, but you can see that the Southern Hemisphere gets a little bit more duration of insolation than we do. Okay, so let's go back to the PowerPoint. Okay, in what season does and on what date does the Earth sunlight distribution look like this? See how it's dark up here and light down here? What is this season? It's the Northern Hemisphere's winter. You got it. Look at that Antarctica. It's all lit down there. Okay. And in what season and on what date does the Earth's sunlight distribution look like this? Where it's, see how it's light up here? There's Greenland. As Greenland rotates, as Greenland moves from here to here to here to here to here to here to here and back to here, okay, Greenland is lit up like all day, 24 hours. So in what season is that? The Northern Hemisphere's summer, okay. And around what time of year is the day-night line kind of vertical like that? See, the Southern Hemisphere is always in twilight. I'm sorry, the South Pole is always in twilight. North Pole is always in twilight. Yeah, this is around the time of the equinoxes. Okay, so March and September. All right. And here's another view of it. 24 hours of daylight up here. Purple would be 20 to 24 hours of daylight. And as it decreases as you get towards the equator. Okay. What line separates some darkness with 24 hours of daylight up here? What line is that? It's Arctic Circle. That's the Arctic Circle. Okay, and that's 66.5 degrees north. Okay. All right, so that's the wrap of the seasons. So that's number 2 on the list of phenomena created by Earth's revolution. The next one is the seasonal change of the visible constellations. All right, so the best way to explain this is go here. Okay. No. Here we go. Okay. Here's the Earth. And here are the constellations that we can see, the equatorial constellations. Now, these are, if you notice, Aries, Pisces, Aquarius. Do you recognize these? Capricornus, Sag, Scorpius, Libra, Virgo, Leo, Cancer, Gemini, Taurus, and Aries. Okay, these are the signs of the zodiac. Okay, these constellations are right in line with the equator. Okay, everyone see how there's the Earth, there's the equator, and if you go out from the equator, they're kind of in line with the equator. All right. So if you know your sign, you might know your sign, you might not. Okay, me, I'm a Cancer. My birthday's coming up on July 3rd. Okay, so Cancer is like June 20th through like July 21st or something like that. All right, right after Cancer is Leo. So you would think that you could see my zodiac sign around my birthday, but you can't. Okay. Your sign is wherever the sun was when you were born. So the house, that's the sun. So if you're a Sagittarius, that means the sun was in your house when you were born. Okay. But this is not a astrology lesson. This is an astronomy lesson. So here's what we got going. Okay. So you know that the Earth is always half lit and half dark. So if the Earth is lit over here, where's the sun? The sun's over here, and we just saw the sun. See, there's the sun right there. There's the sun shining on the Earth. So the Earth is half lit, half dark. And we know that the Earth is doing what under the sun? The Earth is rotating. So all these folks over here, these folks can see these constellations right now, okay? Because you can only see constellations when it's dark out. What constellations can't they see? They cannot see like Libra, Scorpio, Sag. They can't see Capricorn, and they can't see Aquarius. They can see a little bit of Pisces when the sun rises, and a little bit of Virgo when the sun sets. Okay. Now, this is the constellations that we can see in January, or between December and January. Watch what happens when I move the date. There's the Earth rotating. Okay. And we know that we're revolving around the sun at the same time. And so now, this is us right here. We're at the beginning of June, right? Okay, so what are you going to see when you look up at night? You're going to see Virgo, Libra, Scorpio, Sagittarius, and Capricorn. And a little bit of Aquarius maybe when the sun is setting. Okay. You know if you have any of these signs that you were born in the winter, right? But it's summer now. We're coming up on summer. That's because the sun was in the house of that when you were born. Okay, so let me explain. Why do the seasons change? Well, I'm sorry. Why do the stars change with the revolution? Because if this is the sun and the Earth is over here, okay, are there stars in the sky that way? Yeah, they are. There are, but we can't see them because we're on this side of the Earth and the sun's over here. So the sunlight is blocking our view of the stars that are over there. Okay. Where are the constellations that we can see? That way, because that's where it's dark. Okay. As opposed to when the Earth is over here. Okay. Where are the constellations that we cannot see? Well, this way, because the sun's blocking our view of those constellations that are over there. Where are the constellations that we can see? That way. Okay. So the constellations that we can see at night change as the Earth revolves around the sun. Okay, so right now, where's the sun? The sun's on the right. Where are the constellations that we can see? On the left, on this model. Okay, but what we're going to do is we're going to change it. Okay, now the constellations that were over here that we couldn't see, now we can see them because we're on the other side of the sun. So that's why if you look out in the winter sky, you can see Orion. Orion is a really easy constellation to see because of those three stars that are right in a row, the belt of Orion. You cannot see Orion in our summer because we're on the wrong side of the sun. The sun's blocking our view of Orion, right? So the constellations change with the seasons. All right, that's the seasonal changes of the constellations due to Earth's revolution around the sun. Okay, so here's another one. So where are we right now? We are right in here. Okay, so you can see Scorpio, Sagittarius, Libra. What can't you see? Everything over here. You can't see anything over there. Okay. And here's another one. Okay, here's a nice view. Everything over here, like in May, everything over here is blocked because the sun's in our way. Whereas when we're over here, the sun's blocking everything over there. Okay. Here's Orion. This is the winter constellation that I was just talking about. There's Betelgeuse and there's Rigel, a second brightest star in the sky. Okay. And that's a winter constellation. And here are the varying distances of the stars of Orion. So here's the Earth and there's all the stars in Orion. And just note that they're all different distances from us, but to us, it looks like they're all on one black background. All right, so where's the sun in this diagram? If these are the stars that we can see, where's the sun? Well, here's the dark half of Earth. Here's the light half of Earth. So the sun's over there. Okay. And this is important too. We know that all the stars rotate around Polaris once every 24 hours. However, the Big Dipper's position in the sky changes seasonally. So if you go out right now at around 9 p.m., the Big Dipper looks like it's in this area in here. The Big Dipper is upside down. So it's the cup is that way and then the tail is that way, okay? But if you went out at 9 p.m. in winter, it would be way down here. So it looks like it's going to catch water as opposed to spill it out up here. So the position of the Big Dipper or where it is around Polaris at the same time of day. So same time of day also changes as we revolve around the sun. Okay. And the last one is parallax. So I just showed you in the Orion, how some stars are close and some stars are far away from us. Okay. So here's a very, very simple way to explain parallax. So if I'm on one side of the sun and I look up, okay, the stars are going to be in a certain position relative to one another. So here's a close star and here's a far star. But when I go all the way to the other side of the sun, my position of them is going to change. So a really easy way to see what I'm talking about is this. I want you to hold out your thumb at arm's length. Okay, hold out your thumb at arm's length. Okay, I'll do it this way. Can you see? Okay. And I want you to look at something far away. So you can see my sign over there. It says O'Gorman. Okay, I'm going to hold my thumb here. Close your right eye. Close your right eye. And look at your thumb. And your thumb should be in relation to something that's far away. Okay? And then see where your thumb is. And then switch eyes. And what does your thumb do? What does your thumb apparently do? So I'm going to face this way now. Okay, so this is what you should be doing. Doesn't your thumb appear to shift? Okay, and that's only because of the distance between your two eyes. So I want you to think of this eye as the Earth on one side of the sun, and think of this eye as the Earth on the other side of the sun. Your thumb is a near star, and whatever you were looking at far away is a far star. That difference in the near star's position relative to the far star, okay, that's called parallax. Okay, and scientists measure that. And that's another way that we can tell how relatively far away stars are. Okay, so that's another phenomenon created by Earth's revolution around the sun. And that's the little quick lab that we just did. Okay, all right. So I want to go back now and I want to talk a little bit about something that's very difficult, even when we're in school together, but it's pretty important. And then we're going to get to the moon. Okay, so what I want to explain to you now is a little bit about this whole thing that I mentioned called sun's path. All right, so this is actually right here. This is the best diagram. Okay, so I'll give you some. This is you in New York. Okay, and right now we're coming up on the summer solstice, which is June 20th or 21st, depending upon when it happens in the calendar. Okay, and I talked a little bit about this. The sun rises in the eastern sky. It moves up to cross our longitude. That's called solar noon. And then it sets in the western sky. And I explained to you that the only 2 days of the year where the sun rises exactly east and sets exactly west are on the autumnal and vernal equinoxes, or the fall and spring equinoxes. Every other day of the year, the sun rises a little bit off of due east and sets a little bit off then due west. And right now we know that we're coming up on a very long duration of insolation and a very intense insolation in New York because the sun's getting higher and higher and higher in the sky. So this is the sun path that we're coming up on right now. All right. So the sun path that we're at this moment, is, let's see, it's June 8th. Okay. So the sun's path that we got going on right now, it looks like this. So it's going to rise and it's going to go up and it's going to hit solar noon. And then it's going to set like that. Oops, that should be a little bit further over here. Okay. So what's going to happen between now and June 21st is that sun's path is going to get a little bit higher, a little bit higher, a little bit higher, a little bit higher. And then it's going to reach this extreme sun path, which is the longest amount of daylight of the year. And then right after that date, the sun's path is going to then continue. How come I can't change the color? That's weird. Okay. It's going to continue to move downward. Okay. And then when you're sitting in class in September, hopefully we're going to be in class, you're going to be in the high school on the September or autumnal equinox, the sun will rise due east and it will reach solar noon and it will set due west. And that's what's going to happen in September. And that'll be 12 hours of daylight and 12 hours of darkness. And then every day after that, the sun's path will get lower and lower and lower in the sky until December 20th or 21st, which is a winter solstice. And the sun's going to rise south of east, hit solar noon in the southern sky, and set south of west. And that's going to be the shortest amount of daylight of the year. And then every day after that, it'll get a little higher and higher and higher and higher and higher until March, 12 and 12, 12 hours dark, 12 hours light. due east, due west, and they get a little higher and higher and higher and higher and higher and higher and higher until it's next June, and you'll be ending your freshman year, and you'll have our solstice day. Okay, every sun's path for New York, no matter what year it is somewhere between this extreme high path, right, and this extreme low path. Every sun's path is between here and here, every day of the year. Okay, so now we know that, okay, well, on the equinoxes, we have 12 and 12. So it rises at 6, sets at 6, right? Right now, it's like rising at 4:30, 5 o'clock in the morning and setting at 7:30 at night. No, it's not. That's because we sprung ahead. That's because we sprung ahead in spring. So now it's 5:30 and 8:30. That's why we sprang ahead. Who wants the sun up at 4:30 and setting at 7:30? I want it to rise at 5:30 and set at 8:30 and 9 o'clock, right? Okay, humans have adjusted the time by using daylight saving time. Now, what hemisphere is this house in? Well, the noon sun is in the north. The noon sun is in the north. We have to look south to see the noon sun. So what hemisphere would this be? This is the southern hemisphere. Hey, Ranger, pipe down. At approximately what latitude is this house located? Well, it looks like our sun path's just reversed. So what do you think? We're at 41 north, so this would be 41 degrees south, right? Okay. And during which season will the house make the longest shadow at noon? When is your shadow long? When the sun is high above you or when the sun's low in the sky? When is your shadow going to be really long? Okay. Yeah, when it's lowest in the sky. So winter, it's going to make the longest shadow at noon, right? And when is it going to make the shortest shadow at noon? In which season? Summer, right? I apologize for my dog. He's very protective of our house. Okay. All right, and here's another picture of the sun's paths. Just to understand that when our sun's path is really long in the northern hemisphere, what's happening in the southern hemisphere down here? When our sun path is really long, their sun path must be really short. They're winter. When our sun path is really short, their sun's path is very long. They're summer. So that's why we have opposite seasons. The tilt of the earth. Okay, this stuff is very cool, although it is very, don't worry about this. It is very spatial. Okay. All right. So, what I want to do now is I want to take you to Stellarium before we get into, okay. So what does this look like on a daily basis? Okay, I'm going to zoom out. So we're in, well, I have our latitude. I have it in Brewster, but it's pretty much the same latitude. Okay. And that's the sun right now when I'm recording this video. All right. It's like, what time is it? It's like 5:07, okay? So this is 5:07 in the afternoon. And what I'm going to do is I'm going to change the hour. Okay, so I'm going to subtract, no. Okay, I'm going to subtract 1 solar hour. So command minus. Okay, whoop. Oh, I'm subtracting time. Look at me, I'm magical. Okay, whoop. Okay, I'm going to go over here and I'm going to command minus. Okay, that's sunrise today. Where did the sun rise? Due east or north of east? North of east, that's the sunrise. Okay, note the moon is over here. Okay, so now I'm going to add time. So that's where the sun rose, and the sun's going to rise, make its way across the sky until it crosses our meridian right here. That's solar noon. As soon as it's due south of us, that's solar noon. And then it's going to go. Okay, and it's going to set where? Hold on. It's going to set, not due west. Where is it going to set? North of west. That's our summer sun path. Okay. Now I'm going to zoom out, and I'm going to do this. Hold on. I'm going to do this, and I'm going to do it one more time. Okay, I know this is a really weird view. Okay, I'm going to minus. Okay, that's the sun rising north of east. So this is like our dome. Okay, I'm trying to make this look like our dome. So this is going to be the sun going across our sky. Boom, 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 boom. That's our sun path. Now what I'm going to do is I'm going to bring the sun back to due south. And I'm going to show you the equinox. Okay. So now I'm going to add weeks check this out. This is what's going to happen now. So I'm going to add weeks. Where's the command? Darn it. Oh, here it is. Okay. Okay, that's next week, the week after. Notice the sun's getting a little higher. And that, look, I'm adding, now look at the date down here. See, now we're in August 24th. So the noon sun is going to get lower and lower. Just keep an eye on this date, okay? Lower and lower and lower and lower. Now we're in September. That's around the time of the equinox, okay? Lower, 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 up to November, December. That's the summer solstice right there. The winter solstice, okay? So that's the noon sun getting lower and lower and lower. Now check this out. Now I'm going to subtract hours now. Subtract 1 solar hour, control minus. Okay, control. Where did the sun rise? Did the sun rise due east on the winter solstice? No. The sun is rising south of east, and it's going to go to the rise to the southern sky and then set south of west. Look how short that sun path was. That was crazy. I'm going to do that again. Hold on. Hour. Look at how short and low the sun is in the winter. Isn't that crazy? You don't realize it until you see it in stellarium. So again, that's our winter sun path. And this is our winter sun path. Okay. Now what I'm going to do is I'm going to go back to September. Okay, let's go back to the equinox. Okay, right around there. Okay. So now, so here's our equinox sun path. Okay, so it rises due east. Sun rises due east, moves across the sky, crosses our meridian in the south, because we always have to look south to see the noon sun, and sets due west. And those are our 3 sun paths. Okay, so we're not going to draw them like we would normally, but I just want you to understand that's when I say sun path and the suns and the intensity of insolation and the duration of insolation. That's what I mean. Okay, and then so now we're going to go into the moon. And the only thing that we're going to talk about today is how we think the moon was created. And then we're going to get into eclipses and tides and phases. Okay. So this is what scientists hypothesize. Approximately 4.6 billion years ago, Earth collided with an object the size of about Mars. And the Mars is about a quarter of the size of us. It's smaller than Earth. It's believed that the Earth had a hard crust, but the inside was mostly still molten rock. So when it hit it, it was like a water balloon, kind of like the shell broke and all this liquid hot magma came out, right? And got caught up in our gravitational pull, gravitational field, and all this material started coagulated, and that's how the moon was born. So the moon, they believe, was born of Earth, right? And here's what they think happens. Now check this out. There's the Earth's axis. Here's the impactor. That was approximately the size of Mars, they think. This, they think, was 4.2 minutes after impact, 8 minutes after impact, 2 hours after impact. There's the blob leaving the Earth. Now, all this material got caught up in Earth's gravitational field, started orbiting Earth, coagulated because of gravitational forces coming together because it had mass, and that's why they believed formed the moon. Ladies and gentlemen, why do we have a tilt? They believe that Earth's axis was perpendicular to our orbit. When we were impacted, the Earth got knocked off kilter. That's where they think our tilt came from. And that's why we have seasons. Okay? And then here's an artist's conception of, they believe, what happened. There's the impactor. All right? And here's a picture of Luna. Lunes, moon day. Lunes, lundi, moon day, Monday, moon day. Monday is moon day. A month is a month. A month is called a month because of the moon. Okay? So these dark areas on the moon, these are called maria. Mar is sea. So these are old basalt lava flows. Okay? And you can see all the impactors on the moon, the craters. See how the moon has a ridged surface. Okay? And again, let's go over this one more time. Since the moon has no atmosphere, its surface is covered with impact craters for 2 reasons. What's the first reason? There's no atmosphere, so there's no what. They won't do what? Meteors will not do what as they're approaching moon? Friction. They won't burn up. There's no atmosphere to burn up in. 2, what happens on the moon? stays on the moon. Why? Because the moon has no atmosphere. Therefore, there's no agents of weathering and erosion. So all those scars that were made are still there. The footprints that the astronauts left on the moon, still there. The tire tracks that they left from the moon buggy, still there. All right. Okay. So this is what we're going to get into next, moon motions. All right, and that's going to be the wrap up of astronomy. That's what we're going to wrap up the year with. All right. So you're going to answer some questions about seasons and things like that, and I will see you guys next time. Bye.